mean mode, standard deviation, interquartile range, other things of that nature. So we'll talk a little bit about how to calculate those. I will show you how to calculate, how to calculate each of those things, first of all, by hand, but also using Excel. And the method, if you use Google Sheets, is essentially identical. Google Sheets does almost everything Excel does, and I think even the commands are basically the same for what we'll be doing. Yes, and then at the end we will conclude with a discussion of standardized measures, so how we can compare things that may not be in an identical population, but that we might still want to have some comparison point for. And we'll talk about something called the empirical rule that gives us a feel for how understanding the mean and the standard deviation can describe the structure of certain well-shaped sets. Okay. So let's get started. This is split into two pieces, but the second piece is a good bit bigger, so we'll likely take a break after the first portion, the displays of quantitative data, and then a break about halfway through the summarizing measures of center and spread. Okay. So, most of what I'm going to be talking about here are descriptive statistics that apply to quantitative data. So, in order to do the things that I'm talking about here, you need to verify that you are actually dealing with a quantitative variable. And specifically, one good way to do that is to make sure that the units of measurement are known here. All right. So, in order to build a histogram for a quantitative variables data, what we do first is we sort that data into specific ranges. We kind of partition the overall range for the values into something called bins. And the number of values that we see in each bin is the height of the bar that we will plot. Okay? And we'll plot that against each of the bin ranges. The display that comes out of that is what we call a histogram. It looks a little bit like a bar chart, but there are some differences. It's really important for histograms that there not be a space between the bars. Now, obviously, if there's a bin that's empty, it will look like there's a space, but you should think of it as almost like graphing it inside of the XY plane. So there's no gap between different values. Whereas what we call a bar chart is typically used for qualitative data, categorical data, and in that case, we are still counting the number of occurrences of a single value, but we separate those bars out. We always have a space in between each separate bar, and that's to emphasize the fact that there's not really necessarily a natural ordering in that same sense. It's not a quantitative variable. Okay, so this data is actually a little bit dated. It's about 5 or 6 years old, but I'm still going to go with it as written. So the example that I'm going to use here comes from a different textbook. There were 1,318 earthquakes in recorded history as of that time that were known to have caused tsunamis, and again, about which we have data. That last part is also important. We can't really include it in our data if we don't have data about it. Okay, so this is an example of a histogram then, representing exactly that data. You'll notice here on our horizontal axis, we are sorting these by magnitude, and then on the vertical axis, we have the frequency for each magnitude. So how often did we see a value in that particular range? So this is actually measured on the Richter scale. Can anyone tell me what the bin width here is?
Would it be a half?
Yeah, 0.5 or a half. You can see that between 6 and 7, for instance, we have 2 entire ranges included. And so this particular bar corresponds to everything between a 6.0 and a 6.5. Okay. Right. And then the height here, looks like it's about 150 or so. So I think in that time frame, there were about 150 that were between 6.0 and 6.5 and caused a tsunami. Now notice, if we were to change the bin size to something like 0.2, we would have a finer scale here, And so we get a little bit more information about the data itself. We can see here that the most common value is between 7.0 and 7.5. If we look a little closer over here, we can actually see that most of those values are even closer to 7 itself. So 7.0 to 7.2 is a good bit higher than the other values around it. Okay. All right, any questions about that? So this is the basic structure of a histogram. Now, one of the important things to be able to do is to look at the shape of this and describe it using some key terms, and so that's where we're headed next. All right, so before we do that, I guess I should also talk about relative frequency. So this is a frequency histogram where we're simply counting how many times we see a certain value in a given range. This is a relative frequency where instead I'm charting the percentage in each bin. But if you look carefully, you can see that the shape here and the shape here are exactly the same. Obviously, we zoomed in just a little bit because of the size on the screen. The difference is simply in the units of measurement. Rather than measuring the count here, I'm measuring a percentage, but as a percentage of the total area under each bar, those numbers are exactly the same. So the relative heights from the 6.5 to 7 bin and the 7.0 to 7.5 bin should be exactly the same in both charts. So it's really just a change in what we're measuring it against or how we represent what each height corresponds to. In my mind, this information is a bit more useful because it gives us the relative distribution between the different bars, so I can tell the difference between this bar and this bar simply by looking at those heights. But I can also look at the actual Y values here, or the actual vertical values, to get a rough count. So that's a little bit more information than simply the percentage would be giving me. So this is a relative frequency histogram. And again, the key difference is that it replaces the count that we had before, the frequency in each bin, with the percentage of the total number of cases that are in that bin. In terms of the picture, it looks exactly the same. The only difference is the unit of measurement on the vertical axis. Okay. So how many of you have seen stem and leaf displays before this class? I'm just curious. A few of you. So a stem and leaf display also displays the shape of the data, but instead of just a bar where we don't know if all of the values are on the lower end or on the upper end, which, go back a second, as we saw here, this bar between 7.0 and 7.5, we can see that it's the largest one, so most of the values are in that range. But we didn't see from this version that most of them are actually even closer to the lower end of that range. This 7.0 to 7.2 is more common than 7.2 to 7.4, for instance. The stem and leaf display gives us even more information because it actually gives us the specific values within the bin. We can visually see which bins are more populous, I guess is the word, more frequent, have a higher frequency, but we can also see the specific values that are included as well. So the way we build a stem and leaf display, typically when we do this, we're doing it by the number of digits. And so our bin width is going to be 10 in most cases. When I look at this data set, 71, 56, 66, 56, 72, 73, 68, and 82. Let's see, that's 1, 2, 3, 4, 5, 6, 7, 8. Yes, 8 values. I can create a stem and leaf display in this way by first looking at the first digit, and the smallest first digit that I see here is 5. Right, I have a 56, and then there's another 56. So what I do is I write the first 56 by putting it in the 5 row. This bar says, here's where my individual values began. And then the 6 is the ones place for that number. So this is a 56. And then I go through until I find another number in the 50s. 56. So there it is. And there's no others in the 50s. So that's my first row. My second row is the numbers in the 60s. So I look through, I have a 66 and a 68. So in my 6th column, my ones place, my first number is a 6. That corresponds to the 66. And my next number is an 8. That corresponds to a 68. And then for the 70s, I have a 71, a 72, and a 73. Oops. So I put a 71, 72, and a 73. So I can see the 3 data values here. And then lastly, an 82. And I should mention it just worked out that within each group of 10, these numbers happen to be in order. You always want to write them in increasing order here. So I don't want to do 73, 72, 71. I'm going to do 71, 72, 73, just because it makes sorting things out a bit easier. If you look at it sideways, you can kind of see that if I treated this as my band for the 50s, this is my band for the 60s, this is my band for the 70s, and so on, this is kind of like a histogram where the number of entries in that row corresponds to the height of that row. So I can kind of see a sideways histogram by looking at it that way. That's one of the values of stem and leaf, is that it does provide the same information as a histogram as long as your bandwidth is specifically 10. But it also, in doing so, gives you the specific values themselves. And it's, again, a quick way to rewrite this because, for instance, the 71, 72, and 73, I only have to write the 70 once. And it's just the ones place that I write for each extra element. Saves me a little bit of writing, not so much with 8 elements, but with 20, it's a significant savings. Okay, so I did say that one of the important things we should be able to do with histograms is to look at the shape of the picture that the histogram produces and then describe it verbally. Okay, so I mentioned a few minutes ago the largest bar here, the largest bin, is between 7.0 and 7.5, so that's what we would call the mode for this distribution. If you remember modes from numerical data sets, it's related. The mode is the most common element in that situation, so you can think of it as the most common bin in this case. When I look at the shape, one of the things I like to do is to ask, how many modes do I see? Okay, now these don't have to be exact. Certainly when we're looking at a numerical data set, there's a specific way to calculate which one is the mode, which one is not. And if there's one more of a single number, then that's the mode. But in real-world data, we tend to be a bit more flexible. We tend to look more at the approximate distribution. 2 bars that are relatively the same, we treat both as potentially modes. So in this case, I would say that there is one mode, and so this is what's called a unimodal distribution. It has one mode. Uni means one, unimodal means one mode. Another thing to be careful about with histograms is when you're deciding about this modality, think about blending those boundaries a little bit. And part of that is because where I choose to cut off my band might change the shape ever so slightly. But if the peak distribution is somewhere here around 70, if I were to change my bends a little left or a little right where they are, the shape should be roughly the same. So if I had 2 bars that were the same height right next to each other here, I would still call it unimodal. Right? Even if they're just a little different, it's because what I'm saying is that right there in the middle between them would be where my mode is. If I'm going to say that it has more than one mode, what I'd like to see is 2 distinct peaks in the distribution. Okay. If I do have that, that's what we call a bimodal distribution. And so here's a nice example of that. This is clearly bimodal because I have a peak here and then another peak here. I would say maybe somewhere between these two, but most likely in this one itself. But it's clearly 2 distinct peaks. Okay. And there's no reason why we have to be limited to 2 peaks when we look at a large data set in particular. We could have multiple peaks. Okay. So we could have a situation where we're counting cars in a collection of parking lots, and some of them have a significant number and others do not. Or some frequencies occur fairly often and some occur less often. That's the better way to say that. The terms we use are unimodal, bimodal, and multimodal. So that's the first thing we'll use in describing a shape that's apparent from a histogram. Another thing we will use is how the distribution is spread out from left to right. Okay? So probably the simplest one is what's called a uniform distribution. A uniform distribution is where it doesn't even appear to have a mode, and the distribution is the same across all of the bends. Okay? And again, it doesn't have to be a perfect equality. This is definitely something we would call uniform distribution because the values are all approximately the same. When our counts here are in the 40 to 60 range, and they're almost all about the same. I think the highest here looks like about 56, and the lowest is 40. That's a pretty uniform distribution. If it helps, one way to think about what the word uniform is saying, from the Latin, una means one and form means shape. What it's saying is it's all one shape. It's all one form. Okay? And that's actually where the word uniform in the sense of what you wear comes from. It's all the same shape. Okay? You keep that in mind, that will help you remember what a uniform distribution looks like. Another thing we might talk about in terms of, I'm sorry, I thought that was a question. Another thing we might talk about in terms of the shape is potential symmetry. Okay? We will often deal with data sets or distributions that are symmetric. What symmetric means is that if you were to look at one side of the distribution and reflect it across a line in the middle, you should see roughly the same image on the other side, simply in reverse, so a mirror image. If that's true, then we call it a symmetric distribution. And so this is an example where it's symmetric, because if I were to treat this as my line of symmetry and fold the left-hand side over here to the right, you'd see it's not a perfect fit, but it's a pretty close one. This is very close to perfect symmetry. Okay. Again, when we're talking about a data set, we're talking roughly, does it look approximately symmetric? And in this case, it certainly does appear to be symmetric. So this distribution itself is symmetric and unimodal. Data sets that have that property, or variables that have that distribution, are particularly useful, and we will actually see later in this discussion, we can apply something called the empirical rule to many of those. All right, any questions so far? So what if our distribution is not symmetric? Well, one of the most common things is something that looks like it would be symmetric, except it has a longer tail on one side or the other. And what I mean by a tail is the end of the distribution here, off to one side or off to the other. Okay? It is most common that we'll have variable values that are clustered around this central point, and then perhaps they fall off to the left, they fall off to the right. Doesn't happen everywhere. Of course, if we have a bimodal or multimodal distribution, it'll look different. But if we have a unimodal distribution, it might be that it's almost symmetric, but in this case, it has a longer left-hand tail. Okay? And when that happens, what we say is that that distribution is skewed in the direction of the longer tail. So this distribution, we would say, is skewed to the left. Okay? It takes a little thinking, but to be skewed to the left means you have a handful of more extreme values on the left, but most of your values here are to the right in that sense. This net distribution is actually skewed to the right. There are a few extreme values here off to the right that essentially take what would be a symmetric distribution and pull it in this direction. So the way I keep it straight in my head is I think of taking a symmetric distribution, attaching a string to one side, and pulling that string. And if the result produces the graph that I see, then whichever side I pulled to is the side it's skewed to. So this is skewed to the right. Okay. Any questions about that? Okay. So, oh good, we're making good time. By my clock, it's 9:27, and I think we should take a 5-minute break, and then we'll talk about summarizing measures, center, and threat. See you in 5 minutes at 9:32.